Yes, so I guess I was suggested to talk about some special topic. So I think it's I think the common thing to do in this quantum error correction lecture at the very end of the lectures. So today I'm going to talk about some, I don't know, relatively new development in the physics of black holes. And also the phenomenon which is called scrambling. So I guess if you are looking at archive these days, I mean in the past 1 or 2 years, I think you have seen this word scrambling so many times, and also you may have seen out of time ordered correlation functions or SYK model and quantum chaos and these kind of things. And so these kind of things are the topic of today's lecture. But I mean, this is a lecture on the quantum information, especially quantum error correction. So I'm not going to go into details of gravity, but we just use a black hole as a motivation to study certain quantum information theoretic problems. And then based on these quantum info results, we can make some speculations. But so I want to keep the lecture as a quantum info course, but still I think it's nice to talk about some black hole motivations. So yeah, so the question is, you have some black hole and then supposed to exist somewhere, and you throw some quantum state, like a quantum state in the form of qubit, and throw it into a black hole. And then, well, around 40 years ago, I guess, Hawking did some calculation, and he found that this black hole, after some equilibration time, it will start emitting so-called Hawking radiations. And then, but the details of how this Hawking radiation coming out, it's important thing, but at this moment that it doesn't matter. The important thing is that for us, the radiation looks thermal in the sense that it looks like Gibbs ensemble. And then this is very problematic because we originally had the pure state, but now we have a mixed state. So it seems like we are losing some information. And then even worse, actually, no matter what kind of state you throw in, it seems that you get the same state, as long as this energy of the black hole is remain the same. So then this raised this question that is quantum information is lost or not? That is the question. And then well, naively we feel like, yeah, maybe information is lost, but well, we know that quantum mechanics is reversible, so information will never be lost. So there is some tensions, and so of course the goal is we want to construct some consistent theory of quantum gravity, which resolves these paradoxes. But this question has been asked in a more rigorous and precise setting. First by Don Page, so it's known as Page's thought experiment. Okay. So what he considered is the following. So black hole is such a mysterious object. It's a giant and this large object, and then whose dynamics is currently not well understood. So for now, let's assume that, well, this physics, let's just consider the following toy model. Initially, you have some pure state which corresponds to the black hole. so now you can think about just a system of qubits, and then you have some pure state, like very big pure state. And then let's throw in some quantum state. So let's say this is like 1 qubit state, and let's say this is n minus 1 qubit states, so that the total system has n qubits. Then again, as I said, we don't know much about dynamics of the black hole. So we don't know this H and T and so. This is something that's very difficult to study. So for now, let's assume that this U is something random. Okay. Then we just picked one random unitary operator and ask if how this information behaves and so on. Then we wait for a while, and so there are n qubits, and the sum of the qubits will be emitted as the so-called Hawking radiation. And then the question is, can we recover what was the initial state psi by measuring this R without touching R bar? So this is like a remaining black hole. Okay. Now, when we say random unitary operator, there is a more mathematically well-defined. There is a mathematically well-defined prescription, which is called R random. This is, roughly speaking, you can imagine a set of all the possible unitary operators acting on n qubit systems, and then pick one of them uniformly at random. And then assume that black hole's dynamics is actually this random unitary operator. So that's what he considered. So in some sense, we just pushed all of our ignorance of the dynamics of a black hole into this random unitary operator. So that's what he did. Okay. Okay, then he found something very interesting, which we are going to reproduce. But let me just tell you what he found. So this is an n-qubit system, and it turns out that let me check. Yes, right. Right. So if you collect slightly more than half of the qubits in this system, then you can reliably reconstruct this psi state. That's what he found. And actually, the complementary statement is actually collecting where epsilon is small but sufficiently big. Qubits is not enough. Okay, so that's what he found. This is a kind of nice observations, but from the black hole physics context, well, it's just an interpretation, but well, it's like you have some quantum state you have thrown into a black hole. So this psi state should exist inside the black hole. But at the same time, just by collecting all these Hawking radiations, you are able to reconstruct this psi state. Then this sounds like you have like 2 copies of the same quantum state, but this is violating the no cloning theorem. So this is very bad. And then one possible way to resolve this paradox is to say that actually there is no observer who can first reconstruct the psi state outside the black hole, like measuring Hawking radiation and jump into the black hole, and then sort of catch up the psi state which has already fallen into a black hole. That's how people are trying to resolve this kind of paradox. And this idea is called the black hole complementarity. And then but the point is like this precise setting, like qubits and so on, makes this what we mean by quantum information is lost or not lost. But since we have been studying quantum error correction, so let us study this problem from the perspective of quantum error correcting code. So you see that this BH, this black hole state, is something given. So if you look at the entire time evolution, then you have some 1 qubit information, and then you run some unitary operator with some unsure qubits, which is fixed. Then you get some encoded n qubit kind of cold word state. Right. Then now, suppose R, the number of qubits in the R is smaller than n over 2. Then there is a error correction from the complement of R. That is, if R bar contains more than half of the system, then we can reconstruct the original state, actually just by measuring R bar. Well, these are like complementary statements. It's just like more than half or less than half. So in this viewpoint, actually, this what we call the Hawking radiation. Which we call R, is just, it's like loss of qubits. So what we are doing here is that we encode quantum information psi into n qubit system by applying random unitary operator, and then later we emit some of the qubits as quote-unquote Hawking radiations, and ask if the encoded information still remains in R bar or the environment has carried it or not. So that is the interpretation. So in this sense, this problem is really a quantum error correcting code. Now, in the first part of today's lecture, we will derive this famous result by Page. And in the second part, we will talk about more complicated version of the thought experiment, which is due to Hayden and Pletsky, and also talk about scrambling phenomenon. Okay, but for now, let's show this result. So to derive this result, we need to use something called a Schur-Weil duality. And I'm going to introduce certain theorem, which is a bit abstract theorem, but very powerful theorem when we talk about how random and these random unitary operators are random states. So imagine that we have some Hilbert space, which is d-dimensional. So maybe d is actually 2 to the n. And then for the system of qubits. Now, we are going to consider k copies of the identical Hilbert space. So okay. So now, pictorially, you have some physical system you are interested in. So I drew just 10 qubits, but this is the original Hilbert space you are interested in. But now we make identical copy of this Hilbert space. So let me call it H1, H2, and now we will be interested in the so-called permutation operators. So permutation is like, well, if you have integers 1 to k, then you want to permute these guys. So, for example, you can do something like swapping 1 and 2. This is an example of permutation. And this is what we call the cyclic permutation. Okay, but you can think about basically k factorial different permutation operators. And so permutation operator can be specified by this pi. Pi is something which maps these integers to some other sequence of integers. Okay. Now we can extend this definition of permutations to wave functions. So here, Aj runs from 0 to d minus 1. So it's defined on a Hilbert space J. So, then this should transform this wave function the following way. Okay. Good. So this is the definition of permutation operators. And but before even proceeding, I think it would be nice to give a few examples. So first example is, let's see, just let's think about a case where k is equals to 2. So just 2 copies of the same Hilbert space. And then we want to talk about the so-called swap operator. So the initial state here in this equation is A1 defined on the first Hilbert space, and A2 defined on the second Hilbert space. So this is the initial state. Then now we want to apply the swap operator, which looks like this. Just swaps 2 Hilbert spaces. Then attach it to A1 and A2. So this part is a swap operator. which corresponds to pi sense 1, 2 to 2, 1. So it's 1 goes to 2, 2 goes to 1. Then if you follow these trajectories, then you see that you get this this one. So originally we had A1, A2, which becomes A2, A1. So this is a swap operator. Another example is this cyclic permutations. So initial state is A1 on Hilbert space 1, A2 on Hilbert space 2, and kth Hilbert space. So this is the initial state. That's a tensor product. And then cyclic permutation. So 1 goes to 2, 2 goes to 3. Then, right? So 1, 2, k minus 1, k, 1, 2, 3. So this is like how it should look like. Then we attach it to A1, A2, A3. Then the object we get is A2, A3, then A, K, A1. Yes. So this is another example. And, so this is W cyclic permutation. Okay. So this is just a definition of permutation operators and examples. But what we are really doing is that we just permute these Hilbert spaces and in a nice way. Okay, why we wanted to talk about this thing is related to the so-called this sure-while duality. So this is a theorem. So suppose that you have some operator O. This is an operator, any operator, acting on this k copies of the Hilbert space. So it's a very giant operator which acts everywhere on these k copies of the system, and it may have some, it may not have tensor product structure, it's just some. It could entangle different systems. Let's assume that it's any operator. Then, now suppose that this operator commute with k-fold tensor product of unitary operator V for all unitary okay. And here V is acting on each small Hilbert space, like each island. And then you make k copies of them and apply in a transversal way. That's what we mean by k to the V to the k. Now, this statement, just all commuting with this thing, is actually equivalent to saying that O is O can be written like this. And here this W pi is just a bunch of permutation operator. And C pi is just some numbers. So the statement is that this operator, if it commutes with such all of these tensor products, then it turns out this should be written as a linear combination of permutation operator W pi. This is the theorem, which is called Scherr-Weil duality. Okay. Now, is there any question at this point? Clear. Now, let me yeah. Okay. So this is just a theorem. And now, I'm not going to prove this theorem. Actually, it's very difficult to prove this theorem. But this direction in the arrow is very easy to prove. Okay? Because suppose that O is actually written in this form, then we want to show that O commute with these operators. Okay. But this is something easy to prove because O is just a linear combination of these guys. So it suffices to check permutation operator commute with these guys. But like it should, I guess, commute because what we should compute is inverse is equals to this guy. But if we have V, so this is K copy, so it's a first Hilbert space, second case. Then let's say if you apply, yeah, so swap operator here, the undoing with here, then it doesn't matter. Like this line sees V, this line sees V. This is just right. So this is something very easy to see. So this permutation operator commute with such a tensor product operator. This direction is kind of difficult to prove, not easy to prove. But I guess you can convince yourself by trying to find some additional operators. Something. We will fail, of course, but it's actually very difficult to prove this. And then this statement can be proven by some famous theorem. I just write down the name of the theorem, which is called von Neumann. I forgot his spelling, but yeah, something called double commutant theorem. Commutant theorem. But I guess to just get some intuition, I think this direction is enough to sort of see, get some intuitions. Okay, so this is what is called a Scherr-Weil duality. Okay, but now the question is, why is this related to these hard random things? Now, so let me discuss what we mean by how random state. Okay, so how random state means that it is a quantum state psi defined on H, which H is just a single Hilbert space. This guy or this guy, it's just one of them, not the whole thing. And then we pick uniformly at random. But it's not that easy to define what we mean by uniformly at random. So let's, as a warm-up, let's start with some simpler example, which actually not uniformly at random. But first we can think about, let's say, random state from computational basis or Z basis. Computational basis states, which is 0, 1, d minus 1. So all these simple states, like classical states. And then if we pick one of them uniformly at random with probability 1 over d, then that's what we mean by uniformly random over computational basis states. But of course, the Hilbert space contains modern computational basis state. So we should think about a little bit more like bigger Hilbert space. And then another bigger Hilbert space is a set of states is a random Pauli basis state. Which looks like 0 plus 1, 0 minus 1, you know, these guys. Okay, so this one is like a little bit bigger set of the quantum states. But of course, this is not the whole set of the quantum state on the Hilbert space, because Hilbert space, the wave function is continuous. Okay. So now, just as an intuition, you can think about this Bloch sphere. Bloch sphere, yeah. So how does it look like, actually? Yeah. Yes. So this is an example of qubit. So this is just d equals to 2. But what we mean by uniformly at random is uniform distribution over sort of generalized Bloch sphere. So that is okay, cool. So the probability of picking up this point, or this point, this point, this point, all of them should be equivalent. That's what we mean by how random state. And but let's make this a little bit more, even more rigorous, a little bit more by writing down the formal definition. So the probability measure, so this is a continuous probability distribution, so you can write the probability as an integral, right? So integral means like how much you want to put some weight for given quantum state. And then we want to do this in a uniform way. And then since this is a probability distribution, so we want to normalize it like this. So it should add up to 1. But as we have seen in this Bloch sphere example, it's like rotationally invariant. So we want to make sure that this probability distribution remains same as a probability distribution of this guy. Here, this is some unitary operator. So it's just like we rotate the Bloch sphere and then still the probability distribution looks the same. And then, so this part it's a bit sketchy, but you can make this super rigorous if you want. But this is what we mean by Hall random. So Hall random is like invariant probability distribution. Now, with all these things, we can now start computing and proving this page's result. So what we want to do is the following. So suppose that in this page's thought experiment, we have this black hole, and let's say we have input some quantum state 0 state. Then we have some output state. And let's call it psi. Then now, since we have chosen U randomly, so it turns out this psi is also random. Right. So this means that in order to study the property of the code word space, actually we only need to study properties of this Hall random quantum state. Okay. So now, with this observation in mind, what we are going to do is now Hall random quantum state, and also we consider the bipartition of the Hilbert space into R and R bar. We want to compute entanglement entropy on R or R bar. That's what we are going to do. Yes?
So is the V over there the Hall random unitary?
Which one?
In your example?
Here?
Yeah.
Oh, no, it's you can insert V as any unitary operator. So if you use identity, you get the original operator, but you can rotate the Bloch sphere by small theta angle. For example, you can rotate the whole thing by small z axis, and then still the probability distribution should look the same. So this should hold for all V.
So Hall random is a probability distribution.
Mm-hmm, mm-hmm. So essentially, like, we need to make a list of all the possible quantum states, but now it's continuous, so we need to put some weight nicely. Then this weight should be completely uniform.
Okay, but the Hall random here is a Hall random operator, though, right?
Here and here, yes. Right. So there are two notions: Hall random state and Hall random unitary. And so from now on, we are going to only discuss Hall random state because it's much easier to compute. For Hall random unitary, I need 1 more hours to explain. But the point is that if you apply some Hall random unitary to some quantum state, you get a random state. And then, so if you fix the initial state and apply random unitary, then you get the uniformly distributed quantum state over the for Hilbert space.
Oh.
That's something which is implied by this, because here V is like U. Okay, so we want to compute the Haar random state and then compute the entanglement entropy. And then some people have heard that well, this Haar random Haar random quantum state is very, very entangled in the sense that the entanglement entropy is always almost maximal. Okay. Then we want to compute and reproduce this result, but well, unfortunately, entanglement entropy is a very difficult quantity to compute. It's because it's a minus of a trace log law, right? But log is not a linear function. Then, I mean, you can Taylor expand it, but it's really complicated function. So it's actually extremely difficult to compute in this context. So yes, so this is difficult.
Wait, sorry, also, in this case, rho isn't locally distinguishable, is it?
Rho is locally indistinguishable. That is what we are going to derive.
Okay.
Yeah.
Oh.
Yeah. I mean, you may know the answer, but we are going to actually derive it. And, right. So this is not something easy to compute because this log rho is very difficult to compute. But under such case, we typically consider this so-called Renyi entropy, which is much easier to compute. So it has this Renyi index alpha, and then it goes like this. So it's just simple power of rho with alpha. Then this looks much simpler than this one. Okay. And then nice thing is that if you take the limit where r goes to 1, then S1 is actually precisely the entanglement entropy. Okay. And actually, today, what we are going to compute is actually Renyi 2 entropy, S2, which is minus log of trace loss square. So again, entanglement entropy is very difficult to compute. Renyi entropy is relatively easy to compute. And of course, it has some physical consequence. That is, this Renyi entropy is something experimentally you can measure. Well, if you have very sophisticated control of quantum systems. Because the point is, now, in order to so let me explicitly write down what we want to compute, which is a Renyi 2 entropy on region R, which is defined as a minus of log the trace over rho R square. And rho R is defined as a trace over R bar of this thing. And this is Haron. So this is the object we want to compute. So Let me emphasize more. So again, since we are taking square of a row R, we will be dealing with some object which involves two copies of these guys. So we should use k equals to 2 sure while duality. And we will use it later. We will consider two copies of the Hilbert space. Now, let us consider the following object. So right now we have two Hilbert space. And then each of them are n qubits. Then we just consider this object, psi, 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 and then take a uniform integral. Then if we compute this object, like we sort of feel like we can somehow compute this object, right? So let's compute this object. And now, first observation is, so let's see, let me call it F. This F commute with V times V. Well, why? It's because we already know that because of the Haar measure property, we can shift this guy. Right? But these two objects remains the same, which implies that actually this F should have commuted with V times V. So this follows from the depth of Haar measure. Okay. Yes?
Okay, perhaps I'm confused. Rho, are we taking rho squared or rho tensor rho?
Right, so R is like here,
Yeah.
R is like here, and then we compute low R here, and then take a square.
Okay.
And then this is just doubling the Hilbert space is just for mathematical convenience to proceed calculations. The point is, if you know this object, it's actually, there is a way to compute this object. So it's just for mathematical convenience, we are just enlarging the Hilbert space. Okay, so this weird object, integral like psi psi times psi psi, this should commute with VV. Now, nice thing is that it satisfies the requirement for the sure while duality, especially on the left-hand side of the arrow. So you can use it. Therefore, sure while duality says that this F, we should be able to write it as a bunch of permutation operators. But when k is equals to 2, like there are only two Hilbert spaces, there are only two permutations. First is this 1 goes to 1, 2 goes to 2. This is identity, just identity. Or swap. 1 goes to 2, 2 goes to 1. this implies that this implies what? Yes, so this F object, maybe I can write it explicitly again. This integral can be written as something like this. So it's just a linear combination of an identity operator and swap operator. Okay. Now, so we made some progress. So we define this object. This one should be able to give answer to this one, but now we have this form. Now the remaining task is to compute these two numbers. And now for this, we need two observations. First, it's actually Ci should be equals to C swap. The reason is this F. If you multiply F with the swap operator, then it's still F. The reason is because swap operator is 1 goes to 2, 2 goes to 1, and F was just bunch of size, and then so I mean no matter which line you go, it's just so it is invariant under swap. So this is a story for left hand side of this equation, but on the right hand side, if you apply swap operator, then right hand side becomes Ci times swap plus C swap times identity. Then these two things should match, therefore and okay. Now finally we want to fix this C, and then to do that we take a trace of the both left hand side and the right hand side. Okay. Now trace of the right hand side, left hand side, because this is just wave functions, psi. So trace of a pure state like this psi is just 1. So this is equals to 1. So what about the right hand side? The right hand side trace is a bit complicated, but C times trace of the identity operator plus C times trace of the swap operator. But this is something we can compute, and especially identity operator is something which sends first Hilbert space to first Hilbert space, second Hilbert space to second Hilbert space. And trace is an operation which basically connects these lines. And then connecting these lines means that you do the summation over all the basis states. And then there are d different basis states, and then you get so this is d c times this thing plus this is swap and trace. So in this case, we only have one cycle, which means that the contribution is actually only d. Therefore, the answer should be okay. Therefore, actually, we can move this part and then say that C was actually okay. Good. Okay. So we have made kind of nice progress. So yes, let's briefly recap. So what we wanted to compute was this Rennie-2 entropy. And then we observed that for that, we should compute this psi times psi because rho appeared twice. So let's compute this object f. So it turns out f commute with v times v. Then we can use this Schur-Weyl duality and then decompose it into identity operator plus swap op. And then we have found out the coefficient by doing some consistency equation. Okay. Now, finally, let's compute the entropy, well, Rennie-2 entropy. Okay. Now, rho was this thing, just density matrix for psi. And we can sort of pictorially rho is equals to psi. And then here, this is R, and then this is R bar. So this diagram just says that, well, this is a psi, the quantum state psi, and then it's Brand case. So it's just a pictorial representation. And then we needed to compute rho R, which is trace. But trace is just connecting lines and then do the summation over all the this thing. And then so this is a pictorial representation of rho R. Now we want to compute rho R square trace, but basically you need to repeat this object twice. this is R bar, this is R, and now, it's too. Now, in this diagram, so we are representing trace of a rho r square, and the point is this object was rho r, and then this object was rho r. So it's like a big matrix. You multiply them, just connecting lines. And connecting line means matrix multiplication in this tensor calculus. This object is something we need to compute. But now we are almost there because now we have computed the average psi. That's written over there. So somehow we need to use it. And for that purpose, let me just rewrite it in the following way. So this is just a trivial rewriting. No, it's just really a rewriting. Nothing fancy. So basically, I want to move this diagram here. Then to do that, because this line have connected here, this line have connected. So I just shifted this diagram. Then this part is what we have in computing. This F. Okay. Now all we have to do is to insert the expression F into this box. Let's do that. So first, let's just insert identity because it's much easier to do. So, well, it's just really a drawing, but maybe it's better to write the same thing first. And okay, now let's insert identity operator here. So I'm gonna create this guy and then identity like this. Identity. Okay. So then what we have is this is a case for the identity operator. And then now what you should do is this was R, this was R bar, this is R bar. So this is basically counting the dimension of the Hilbert space associated to these lines. So this object is equals to dr times dr bar times dr bar. And of course, this is the counting of the Hilbert space, so this should be the case. And you can do the same thing for swap operator. So for the swap operator, what you should do is you should connect lines like this, and well, you can try that, and then it's a bit complicated to draw, and then so I can just tell you the answer. That is, it turns out the answer is dr bar dr dr. So it looks similar, but the number of r and r bar are just swapped. As a result, we noticed that okay, but using these equations, we can further make some progress and simplify the equation, and let me even simplify the equation. Okay, so this is the result. And then if you want to convert it into the linear entropy, you just take log and then take minus. That's yes.
So in the image above there, we don't have any
Here?
average on.
So here.
Yeah.
Yes.
We don't have any average, but then you're saying that you rearrange it, then it will be equal to where we have.
Oh, right. So actually, right. So now, more precisely, what I have computed is right. So yes. So we take a psi randomly and then compute lower square trace, and then we are computing the average. So you might have a chance of having some state which is product state, and or very complicated state, and then the results are different depending on the state. But what we are computing here is the average over all the quantum states. Okay. So, right. So maybe it's nice to recap a little bit. So we are computing the linear entropy of a random state. But random state is featureless in the sense that it is rotationally invariant. Therefore, we can use this nice sure-wire duality. And it turns out this psi times psi can be written as like I times swap operators. And then the rest is just this diagram calculations, like these drawing lines and counting the number of loops and so on. You can compute. Okay, but you get this result. But now we need to probably give some interpretations. So suppose that R is much smaller than R bar. That's in the black hole context, that is the emitted Hawking radiation is still less than half. In this case, this average of a trace square is because the R is small, so roughly equals to. So here you can neglect dr because it's smaller than this one, and then you get right, and then so it's 1 over dr. Now let's make a comparison. If rho r is identity over dr, which is maximally mixed state, then this trace would be 1 over dr. So for random, pure hard random state, if you compute trace rho r square, its value is actually very close to the value for the maximally mixed state. Here I didn't talk about. So we are only computing this object like trace, but it turns out that if you do this a little bit more carefully, then you can prove that this guy trace R is indeed very close to IR over dr, maximally mixed state, in the sense of the one node. So essentially, if you collect Hawking radiations, which are less than half of the entire system, then what you see is just random, featureless random ensemble. And from such a random ensemble, there is no way of retrieving the initial information. Yes.
Two questions. One, what are the dr bars? Are they infinitesimal changes in the Hilbert spaces? Or?
So right. So let me make sure that let's say this is an R qubit and then an R bar qubit. Then dr is 2 to the n r, and then the R bar is 2 to the n R bar, and d is 2 to the n, which is 2 to the n r plus n r R bar.
Okay. And then the second question is, why are we taking the randomization before we take the log in the entropy?
Oh, right. That's a very good question, and then yes, and so right. So strictly speaking, we should have had the randomization right. So right now, I'm doing the average of this guy, not the whole thing. And then if you want to know the average value of this entropy, then we should have done the integral outside. But again, log is very difficult to deal with. So we cannot do it easily. But actually, since rho r is very, very close to maximally mixed state, in this regime, actually, there are some approximation you can make. And actually, you can rigorously bound these functions, but it turns out that for many purposes, it's actually average of this guy is more meaningful quantity to look at. But so the answer I can give is that it's just for simplicity of discussions. And if we make a little bit more effort, actually, you can compute the average of this guy. Well, I don't know how to do that, but maybe we can do that, but I would suspect that we can only get some approximate lower bound. But that's, I guess, enough to make some conclusions. Yes?
What's the name of like this diagram with these lines? Is there like a formal name for this sort of diagram?
Tensor networks or
Oh,
tensors? If you see box and lines, usually people call it tensors. Right. Okay, so that's like the derivation, this famous result by Page. But I guess now I think more important thing is this sure-while duality is a very special, very powerful tool to compute things when the system is random. And then, so I think interesting thing is that we have fished all our ignorance of the black hole dynamics into this random unitary operator. But once things are too random, we are too ignorant, and actually there are some guess we can make. And then this is kind of example. And then you can sometimes do analytical calculations. Now, before taking break, maybe I want to talk about one more thing, which is actually the topic of the second part of the lecture, and then also, yes. So yes, so let me briefly recap these results from the perspective of black hole information problems. And, I mean, I will just restate the Page's experiment first. So Page's thought experiment was, we have this big box, the unitary time is running upward, and you have input that is qubit. Then you have initial black hole state. Then you have some encoded states, and R was the radiation. Then R bar was the remaining part. And then we show that, well, we need to collect more than half in order to reconstruct psi. Because if rho is less than half, then actually it's completely featureless. So there is no way of recovering the information. All the information about psi should go here instead of here. Okay, so that's the implication from Page's result. But it's like waiting for the black hole. So it's okay. But it's kind of like, well, natural result. But around 10 years ago, Hayden and Preskill has added a very interesting twist to this setup. So instead of a pure black hole, actually what they considered is a black hole which has already emitted half of its content. So it's like they actually consider a situation here, not here. So more precisely, what they considered is like you have some black hole. It has already emitted a bunch of Hawking radiations. And then again, black hole initial state could be viewed as a random state. So if you carry out some of the qubits, there will be lots of entanglement between radiations. Early part of the radiation. So it's half of the content has been already. Now, for such an old black hole which has already emitted half of its content, we are going to throw a quantum state. And then do the same. And then we correct the Hawking radiation again. So this is a, let me make a distinction clear. This is late time radiation. And then they asked, is it possible to reconstruct psi state by correcting R? That was their. then naively we think like, okay, again, we need to collect half of its content and blah, blah, blah. But they considered a very interesting scenario. So I'm not sure if I can reproduce the way they wrote in the paper was kind of interesting. But so Alice has some secret diary which she wants to destroy completely. And then one possible way is to throw it into a black hole. And then, right. Then she has thrown it into a black hole. Okay. Then she thought it's safe. No one can reconstruct. But somehow Bob wanted to read Alice's diary. And then then basically Bob has been stalking Alice. And then, so he actually secretly collected all the early part of the Hawking radiation. And then waited, like he was preparing like for the moment when the Alice throws her quantum diary into a black. And then now, so Bob has access to this part. And then now Bob collects additional Hawking radiations. Then now the question was, having access to this early part of the Hawking radiation, can Bob reconstruct Alice's quantum state easily or no? And it turns out that yes, that's the case. But surprisingly, if this is an m-qubit quantum state, then Hayden and Preskill proved that actually collecting just m plus epsilon qubit is enough to reconstruct Alice's quantum state. So it's just, if Alice's quantum state is single qubit, then let's say you can just collect 1 or 2 qubits. I mean, any qubits from this lots of Hilbert space. You just pick 1 or 2 of them. And then there is a strategy for Bob to reconstruct this size. And this is something called the Hayden-Preskill thought experiment. And I think this is pretty mysterious because, again, Alice has thrown her quantum state into a black hole, assuming that black hole will delocalize quantum information pretty nicely. Like it's a very good encoder of quantum error correcting code. So hides the information very well. That was her hope. But it turns out that because of this random property of unitary operator, it turns out there is a strategy for Bob to reconstruct Alice's state pretty easily. That was kind of surprising. Anyway, yes.
So I guess this is only partly related. So let's say that like n over 2 of the particles have already radiated, right? And let's say Bob didn't bother collecting them.
Okay, yeah.
So could Bob in principle throw mass into the black hole and then observe that new radiation to determine what Alice had thrown in?
Right. But still, if he doesn't have access to this part, then he needs to wait really long time. Well, really means like half of the black hole. It's a long time.
But it would be in principle always possible for him to recover the information if he just kept throwing junk.
Sure. At some point, yes.
I mean, yeah, he'd have to wait a long time, but he could double the mass and okay.
Right. Of course, that is possible. Well, it's actually, you don't need to double the mass because of the Hawking radiation, we think that eventually all of the contents should come out as a Hawking radiation. Well, of course, this viewpoint itself has some puzzling or contradictory feature, but still, it should be possible.
Okay.
So, but I mean, you can throw in more mass and then make it bigger, and then that's also possible. But it takes long time. But this is quite like immediate. Like you throw information, you throw a qubit, but it just immediately reflects back to you.
So then, I guess like relatedly, let's say that Bob has collected enough qubits to decode Alice's diary.
Sorry, what?
Let's say that Bob has collected enough Hawking radiation to figure out what Alice's diary was. Could Alice throw something in, and then no longer Bob would have enough information to determine her diary?
So could you repeat?
Okay, so Bob has collected, n over 2 plus m plus epsilon qubits. Right? Now,
So in this
Alice has found out that Bob has collected that many radiation qubits. Could she throw something into the black hole at that point? In order
to
increase the mass?
disturb. I see.
And at that point, Bob wouldn't be able to determine her diary anymore?
So it sounds like the question you are asking is like another, right?
Yeah, something like that.
Yeah, something like this, right? So if this is more than half already, then it's actually this degree of freedom has some maximal correlation with this one.
Yeah.
So there is already a, I mean, you cannot undo the, so if you want to perturb the black hole, you should do it before Bob collects Hawking radiation.
So if he's collected them but hasn't measured them yet, then her throwing stuff in would increase the effective mass?
No. Because well, I haven't explained this, but the point is that it is a kind of an entanglement between correlation between input and output.
Yeah.
This part, then you can actually more precisely quantify by mutual information between these two degrees of freedom. Now, no matter what you do on this side, you cannot change these values because it's an entanglement property between these two subsystems, and then no matter what you do here, it doesn't. It's a local operations. So you should have done something here. You are Alice, I don't know. Yes. So this is the Hayden-Presque thought experiment. And then it was quite puzzling. And then people started calling this phenomena scrambling. And then, well, people just called it scrambling. And then without having good idea about what is it? Yeah. What it is. So, right. So in the next lecture, I'm gonna talk about Hayden-Presque thought experiment a little bit more. And well, so actually the question, I think the one immediate question is like, how do we reconstruct this quantum state? And when is it possible? And fortunately, there are already some quantum information theoretic answers to these questions. But today, I only talk about this when part. And because if we want to talk about how part, we need more, I mean, 1 more hour to explain. And it's related to something called out of time order correlation function. Okay, so let's take 10 minutes break. So I briefly introduced the Hayden-Presque thought experiment, but at the beginning I'm gonna deviate a bit. And then actually we will be back to Hayden-Presque only at the very end. So now we are going to talk about this mysterious object, which is called out of time order correlation function. Okay, so what is this? Imagine that you have some one-dimensional system of qubits. So it doesn't have to be one-dimensional, but just to be specific, we have a bunch of qubits, and let's call these qubits like set of qubits like A, and then let's call this D. There is some reason why we want to call this D instead of B, but for now just 2. different alphabets. Okay. So it's just an n-qubit system, and then the subregions A and D. And what we call out-of-time ordered correlator is the following. So it is a correlation functions for the following form. OA is an operator acting on region A. OD is an operator acting on region D. But this system has some dynamics, and then the system is time evolving. So A is measured at 0, and then D is measured at time t, A at time 0, D at time t. So in this sense, it is out of time ordered correlators. And just to be very explicit, let me rewrite it in the following way. This is a trace of OA, ODT, OA, ODT, and rho. The rho is the quantum state we are in. So this is the definition, out of time ordered correlator. People often call it auto. And now here, time evolution operator ODT is just U, OD, U dagger. This is time 0, the original operator, and then U is our time evolution operator. This is a definition. Now, before explaining the properties of this out-of-time ordered correlator, so in today's lecture, we are going to make one assumption that is this rho, the quantum state, is actually a maximally mixed state. Okay. This is assumption in a physical language. This corresponds to a Gibbs ensemble, e to the minus beta, with beta equals to 0, which implies that the temperature is infinite. So this is like high temperature limit. We need this assumption to simplify the calculations, but I guess any rho which is in a high temperature regime with short range correlations should be fine. So this is an object we are going to talk about. Okay, but why do we want to talk about such a stuff? And then this quantity has been sort of proposed, so like kind of out of nowhere. Well, there's a like 50-year-old Russian or Soviet paper which actually does study this, but after that, no one followed up this line of researches until like 4 years ago or 3 years ago. Staff found out that this is actually a good quantity to study. But let me explain why this quantity is a good probe of this phenomenon of scrambling. And by the way, I haven't defined what scrambling is. So it's more like we want to find a good definition of scrambling by using this out-of-time ordered correlation function. So, right, so this is the correlation function. So now, suppose that this system is interacting with some local Hamiltonian, and when t, small t, we expect that the ODT is a small operator. Why? It's because if OD was, let's say, one body operator, and time evaluate for a short period of time, then its support of the operator range grows only a little bit. And we have seen this in this discussion of the circuit depths of the quantum state. But the point was that if we do the UOD U-Dagger with some short depth circuit, short depth means like you can apply it in a short period of time, then actually it's only supported on these, in this example, these 4 qubits. So there is like light cone, and here its identity. For this reason, when T is very small, and this is region A, this is region D, and then ODT will be supported on some region localized near the original region D. Now, if this is the case, then OA and ODT have no overlap at all. Therefore, this weird ordering does not matter. So this out-of-time ordered correlation function is actually, well, it was OA, ODT, OA, ODT, which is, because these guys commute, no overlap. Right. Now, for example, if OA, OD are some simple Pauli operator, like Pauli X, Pauli Y, and Pauli Z, then this auto should be equals to 1. Because square of the Pauli operator is identity, square of the time over the Pauli operator is also identity. So that's fine. So for a while, this quantity is just unity. Then it's pretty boring at the beginning. But when the system time evolves, what is, yeah, system time, large T, what we are going to see is we have this one-dimensional line, A, D. Now, support of D becomes as big as the system size and then starts to overlap with A. Then OA and ODT no longer commute with each other. Then now, at this point, this weird ordering of time should matter. Okay. Now we can make some speculation with the behavior of this auto. So suppose that this ODT is supported on this entire region, this blue region. Then we can always decompose any unitary operator or this Pauli operator, time-evolved Pauli operator into usual Pauli operator. And here by Pauli operator, I mean it is some object which looks like here, something like that. It's just a string of Pauli operator, X, Y, Z, or sometimes you get identity. Then you get. It is always the case that given any operator, you can do this decomposition. Now, when this ODT the size of operator grows, then it turns out that this decomposition or this linear decomposition will be dominated by high weight Pauli operators, whose weight is, well, as big as this length, right? Well, length times 3/4. So ODT is just a bunch of big operators. Now, if we compute this object and assume that OA is Pauli, then the point is that the Pauli operator can, yes?
Oh, sorry. For the dominated by high weight Paulins, what does that mean? Because you can just decompose a high weight Pauli into a sum of low weight Paulins, right?
Right, so let me clarify what I mean by this. So in that example, ODT, the support of the ODT is 4 qubits, which means that I should be able to decompose ODT as Pauli operator of the following form.
Yeah.
P1, P2, and then other guys are identity.
Yeah.
And then now as time evolves, what I mean by high weight means that the number of non-identity elements becomes bigger. So in this case, so this is summation of lots of Pauli operators, but most of them has lots of supports.
Okay.
That's what we. Now, very roughly speaking, now if you have Pauli operator, 2 Pauli operators, they could commute or anti-commute. And when we commute, it's like if you have x, it's I, but if you have x, z, you get -1. So it turns out that if you compute this object, there are some contribution which is like +1, -1, +1, -1, sort of randomly. Then all these contributions get cancelled, and then this becomes almost 0. Now, let me repeat the argument because it's kind of important. So when OD and OA commute, all the contribution gives me +1 because it's commutations. But if I have some Pauli operator which anti-commute with OA, that one gives me -1. But +1 and -1 sort of appear randomly because this CP is kind of random variables. Therefore, all these phases, +1, phases, are get cancelled, and this value becomes very small. So the point is that originally we had this auto, which is 1, but at late time, this value becomes small. And that is a kind of a signal that you add some perturbation locally to D, and this perturbation grows, and it reaches the region A, and then this out-of-time ordered correlation function somehow detected the initial perturbations. So in this sense, people believe that this is a measure of a quantum chaos, because chaos is like you have 2 identical objects, and then change one of them a little bit, and then time evolve it, and then at late time you see something very different. Like it's like I cough here, and then that could lead to some tsunami somewhere in other country. That's the butterfly. But like tiny perturbation kind of like amplify. In some sense, it's a kind of quantum version of this phenomenon, because we add small perturbation locally to region D, and at late time you see the effect very clearly by seeing this out of time order. So this is the kind of the argument. So for this reason, currently what people think is that the scrambling, so what we mean by scrambling should be associated to decay out of time ordered correlation function. So when we say that system has been scrambled, means that the system has time evolved a lot, so that these out of time ordered correlators, these choices of A and D, it becomes very close to zero. Okay, now that's good, but again, we have started this discussion by talking about Hayden-Presque thought experiment, and then somehow I suddenly switched the topic and then started talking about out-of-time ordered correlators. But now we want to relate these two notions, and it turns out that well, this OA, we will eventually show that this OA characterizes some degree of freedom for input, and then OD characterizes degree of freedom for this late time Hawking radiations. But we will see. Okay, where is it? But to make this relation very explicit, I need to recap one technique from quantum information theory that's called Choi representations. And well, I think by now many people have heard of these Choi representations, but let me recap it. So in fact, what we need is the simplest version of these Choi representations. That is, suppose that you have some unitary operator, n qubits. So suppose that there is some unitary, then this object U can be viewed or interpreted as a pure quantum state on 2n qubits, doubling the Hilbert space. That's the Choi representations. And how do we do that? Well, there are many different ways to define. I mean, there are different ways to explain it. There is only one way to do it. But, I can write down unitary operator with each component very explicitly, like Uij with I and j. Now, let me call U state is just some numerical factor. D is a Hilbert space dimension. I and j, U, I, j is okay. So I just flipped the blur to ket and then added this mark by doubling the Hilbert space. So it looks like a pretty trivial rewriting, right? And now let me explain this from two more different ways. So one method is just It's actually this U. This definition is equivalent to the following. Where EPL is this special state which are maximally entangled. Okay. So, right, so you have EPR pairs, and then feed one of the system, one of the Hilbert space into this box of unitary operator outputs. And then on the other hand, this right hand side you don't do anything. It turns out this is exactly the object. And you can check that this is the right definition by inserting this into this. Like, well, okay, you can derive this. This is what we mean by viewing U as a pure quantity. If you are familiar with language of tensor networks, then you have tensor with input and output, but you can just bend the tensor leg and then do this, and then make both of them as like output. But this is essentially like similar to putting EPR pair time evolving it. Okay, this is Choi representations. And yeah, so why are we talking about Choi representations? That's because this allows us to view black hole time evolution or any many-body physics time evolution as a quantum state. So let us look at just a few examples. So if unitary operator is an identity operator, then it's a box of identity. It turns out its state representation is like a bunch of EPR pairs. This is, I think, very natural from this definition, because if you take U to be identity, then you get just EPR pairs. And in some sense, this makes sense, I guess, because whatever you do on the input degree of freedom should be maximally correlated with output. So if you change the state of the qubit here, then it should affect output. So I think it's a very natural way to represent identity operator. But if we have a swap operator, which two qubit swap operator, then it turns out that you have EPR pair like this. So this EPR. Now the difference is that these two are forming EPR, these two are forming EPR. And again, I guess it makes sense because whatever you do on this qubit should affect only this qubit, not this qubit. So like you see the correlations in time very explicitly. But identity and swap are very trivial because it's sort of non-interacting. And then it turns out that if you have U, which is random unitary, then it turns out this state representation, the Choi representation, you have this four-partite states, and then this is a very complicated multipartite entangled state. It's always maximally entangled, almost maximally entangled along any bipartition. Okay. Now the reason why we want to do this is because what we want to use this to discuss the black hole dynamics. Any questions? Is it fine? All right, so now we can finally see the connection to Hayden-Presque. So this is again the black hole dynamics, which we do not know much, and let's see. Let's call these guys A qubit, these guys B qubit, then these guys D qubit, and this C qubit, then time runs upward. So this is a unitary operator. Now we can write the state version of this unitary operator. That is have this 2 qubit here. This was A, this was B. Then so this is like A bar, A prime, and then so B prime. And this is EPR. Now let us have some interpretations. First of all, A is Alice's quantum state psi. That's the place you put Alice's quantum state. And then you could view A prime as a difference. So it's like a logical qubit you have for reference. And I guess we have used this technique to prove like singleton bound and so. Then B and the B prime. This is like in the case of the Hayden-Presque. This is like this black hole and RE radiation. Then which has lots of entanglement because we have already emitted half of its content. So it turns out this state representation of this unitary operator is precisely the situation of the Hayden-Presque thought experiment. That is, A is Alice's input state, B is the black hole, as well as its entangled partner, the RE part of the Hawking radiation, and then C remaining black hole, and D is the late time radiation. Okay. So this is precisely the reason why we wanted to do this state representation of the things. Now, with this state representation in mind, we can make the following observation. So first, Page's thought experiment. Asks if we can reconstruct Alice's quantum state just measuring Hawking radiation. That is basically we are interested in the mutual information between A or A prime, more precisely, and B. Then this object is this. Right? And if this quantity is very big, then there is a way to reconstruct Alice's quantum state, okay, just by measuring Hawking radiations. And then we have seen that, well, we need to collect around half of it. And so, or maybe, in this case, more than half. But Hayden Presskill consider the following, because Bob has an access to both early part of the Hawking radiation and the late part of the Hawking radiation. So what he has an access to both B prime and D. So what we should study is the mutual information, the correlation between A prime and okay. And what Hayden and Presskill actually proved is that this quantity becomes nearly maximal if unitary operator U is a Haar random operator. Okay. Any questions so far? Now, finally, out of time ordered correlator and Hayden Presskill. So we have started from this weird thought experiment from Hayden Presskill, like black hole has radiated half of its content and then try to reconstruct it by collecting just a few qubits. And this is the situation. So this is Alice's input state, black hole, early part of the Hawking radiations. This is the Hawking radiation, remaining black hole. Now by using entropic quantities, we can make this statement of reconstructability very precise. Okay. Now finally we want to talk about out of time ordered correlation functions. I defined out of time ordered correlation function by using OA and OD. So we will be interested in OTOC, OTOC, acts on A and acts on D, and then D is at time T. Okay, so I'm going to compute out of time ordered correlation functions, but I'm not that particularly interested in this value of out of time ordered correlation function for particular choice of operators. I'm rather interested in generically how small it is. So, for this reason, instead of this object, I'm going to consider an average all Pauli operators. Actually, any basis operator is fine, but operators on A and also D. Now, let's say that A contains NA qubits. D contains ND qubits. Then there are 4 to the 2a Pauli operators, because I, X, Y, Z, and there's anyway copies of them. 4 to the and the Pauli operators. So what we are going to compute is this out of time ordered correlation functions average. That should look like this. Okay, so this is what we are going to compute. So we are just interested in like how generically small this out of time ordered correlation function is. Is there any question about this definition? Now you may think that this quantity depends on like details of the systems and details of the Hamiltonian and so on. But for this particular quantity, so you can compute things analytically, and it turns out the following theorem holds. And log 2 of the sort of average equals to where this object is linear to mutual information. Okay, so this relation always holds. Yes.
Sorry, is that a minus sign or like?
It's a minus sign.
Okay.
Yes. And now if you haven't seen this formula before, I guess you should have actually been very surprised. But the reason is the following. This out of time ordered correlation function only talks to A region and B region, like A and D. Both of them are outside of the black hole. But if you compute its average, then it turns out you learn something about B, for example. It's a correlation between A prime and B prime D. But B is like degree of freedom related to black hole. So this is some mysterious feature of this out of time ordered correlation functions. But one interpretation is, of course, we are speculating that scrambling implies or implied decay of OTOC. But if we assume OTOC decay, which means that we feel that this is small, but if this quantity is very small and very close to zero, then this part, including minus sign, becomes very big. So, because this thing is small, This means that well, linear to mutual information is very good. Therefore, relative mutual information and ordinary mutual information is slightly different, but in this regime we are looking at, this infinite temperature regime, actually they behave in a kind of identical way. Well, they are essentially give you the similar properties. So this means that there exists some strategy for Bob to construct psi state. So for this reason, by looking at this out-of-time ordered correlation functions, which are probably a good measure of scrambling, you can say that this Hayden-Prescott type thought experiment is possible. And actually, like this out-of-time ordered correlation functions, there are some analytical calculations you can do for toy models of black holes, and then people have found that these values actually becomes very, very small. So from that, we can deduce that in actual black hole, there is actually a strategy, like in that this Hayden-Prescott thought experiment is possible. Now, let me briefly derive this out-of-time ordered correlation function formula. And well, I'm going to only sketch the proof. It's a very easy formula to prove. And one thing we need to use is the following lemma. That is, if you have Pauli operators, then take an average. Well, I could put dagger, but it's same because it's emission. Then it turns out this is same as taking trace of O operator and then replacing it with identity. And graphically, it's just P operator, then taking an average is equivalent to do this. Connecting a line is trace, and a straight line is identity operator. Now, with this thing in mind, we can derive this formula, and now out-of-time ordered correlators should look like this. Now we have OA operator here, OD operator here. Maybe I should big font. B, OA, OA, OD. And take a trace. So essentially, this is the object we need to compute. So this is ODP, sandwiched by U and U dagger. This is P. Now we are going to take some average over OA and OD, and then we use that kind of relations then to get the following diagram. No. See if it- Yeah, something like this. Then maybe it's better to write down the degree of freedom, maybe CD explicitly. Okay. So essentially this is the object we need to compute. But we already know that this box U can be interpreted as U, and then this U dagger can be interpreted as this which blanket, and then so row is like U and U dagger. So it turns out this entire object is a row, but we are connecting these two lines. So traced over A and C. And this is row BD. Then you have same object here. Therefore, this entire diagram where we have computed out of time ordered correlate is proportional to, well, up to some numerical factor, it is proportional to trace row BD squared. But we already know that this is related to linear to entropy. And then if we actually massage the expression a little bit, you can derive that formula. So this is the derivations. Any questions? Right. Okay, so right, so this is like the derivation of out of time ordered correlation function, its relation to linear to entropy. So the upshot here is that Haley and Presque prove that if U is a Haar random unitary operator, then it is possible to reconstruct Alice's quantum state. But it turns out that we need only a much weaker criteria, that is just decay of out of time ordered correlation function is enough. And it's because of this formula. When out of time ordered correlator is very small, we can prove that linear to mutual information becomes very big, which implies the existence of the strategy for Bob to reconstruct Alice's quantum state. Now, that's good, but because as I said that this quantity out of time ordered 4-point correlation function can be analytically computed in actual physical systems, which are related to black holes. But one obvious missing piece of this line of researches was that it's actually how. So what Haley and Presque did and this theorem did, so I derived this theorem around 2.5 years ago, and at that point I didn't know how to construct actual recovery procedures. But so more recently, we came up with some nice solution that is it's actually we found out some deterministic protocol to reconstruct Alice's initial quantum state, provided that this out-of-time ordered correlator averaged is very small. And this protocol is kind of cute because it uses it incorporates the idea of the Grover search algorithm. Somehow you find the Alice's quantum state nicely. Yeah. So that's my very recent paper with Taif around 3 months ago. So in this sense, this problem has some nice solution from quantum info perspective. But of course, this paper by Hayden and Preskill was a starting point for people to start thinking about what is scrambling and what is quantum chaos, what is black hole, and so on. This sort of became like a very big research area for string theorists. So I think it's nice that sometimes quantum information theory is not just for quantum computers, but sometimes it has some very huge impact to people outside quantum information theory community. Okay, so I think that's all the things I'm going to talk today. So maybe if you have questions, please ask me. Yes.
So does this have any like consequence or implications for quantum error correction?
Consequence from quantum error correction?
Yeah, or implications?
Implications. So you could, of course, view this thing as a quantum error correcting code. I mean, always, in the sense that. So we should interpret this object like this A prime is a reference. So let me just remove this part. So A is the input, and then you have 3-party output. So you prepare some quantum state and then prepare logical encoded state. And then the question we are asking is like, we encoded the quantum information is 3-party, and then when can we reconstruct Alice's quantum state? And then Hayden and Preskill result says that, well, having access to D and B prime, yes, it is possible. But of course, if we collect both C and D, it is possible. Then it turns out that collecting any 2 of 3 is enough to reconstruct Alice's quantum state. And then this is actually the very identical to the situation of quantum secret sharing code, the 3-party quantum secret sharing code. That is, any single party cannot reconstruct the quantum information.
But in like let's say a quantum computer, wouldn't you really only have access to like C?
Oh, we actually
Because D and B are like the environment. Well, I think, can we think of it as like the environment?
maybe it depends on the observer. So like I think to some extent the answer is a bit sociological, but I feel a bit safe to study these systems like black holes by putting people at asymptotically infinite, and like so that like you have a black hole and then you cover it with some like perfect mirror, and then you try to represent all the physics inside this mirror, inside the black hole, by using this boundary degrees of, it's like holographic principle. In this case, we can discuss everything inside the black hole by using boundary degrees of freedom. Then it's pretty well defined. And then for that perspective, I guess B prime and D are the physical degree of freedom I have access to. But there may be some observer who like just collect D and then jump into the black hole and then measure C. That also sounds reasonable. It's just your reference frame you want to pick. I cannot think of any observer who has access to both B and C, but but I think the important lesson here is that information is delocalized over 3 regions, and then it's delocalized, and we cannot say like, oh, information is inside the black hole or outside the black hole. So previously, people thought that this black hole and quantum cloning problem, we tend to think like, oh, information is here or there. But in this case, even this way of thinking could be misleading. That's one lesson we can learn. But I don't know if it has some practical applications. Oh, actually, well, I'm not sure if it's practical or not, but so I came up with actual decoding protocol to reconstruct this psi state. And then, but this decoding protocol works if unitary operator is actually a unitary operator. If unitary is actually, this dynamics is not unitary but some dissipative dynamics, then this reconstruction procedure shouldn't work because the information I throw in will be destroyed. So then, so actually in a laboratory experiment, which could be done in 20 years or 30 years, let's say we want to measure this out of time ordered correlation functions, and then, okay, maybe some of you are experimentalists and you come to me and here's the data, then you see like, okay, this OTOC is decaying. But then I cannot believe the data. That's because the signature of scrambling is decay of OTOC, meaning like seeing nothing is the signature. It's very bad. Because, I mean, I can do some stupid experiment and then, like, I mean, I can easily see nothing, right? So it's very, very difficult to say, like, clearly say, like, it is scrambling is indeed happening. But it turns out that by actually running this decoding protocol or reconstruction protocol, we can say that decay out of time ordered correlation function you measured, it's actually not coming from noises or decoherence, but it's actually coming from unitary scrambling dynamics. So this way of thinking on this decoding protocol may have actual advantage of serving as a genuine measure of scrambling. Because all these calculations I mentioned assumes that U is actually a unitary operator. So this thing that's by running this reconstruction protocol, you could. Yes. And then actually I have been talking to some experimentalists, and then they actually implemented this decoding protocol for very, very small systems, and then so we have some decoding experiment which should come out soon. Yeah. So these things may have some applications. I think it's nice because we are studying this weird object because we wanted to know if black hole is unitarily evolving or not. And then we still don't know. And maybe it takes 100 more years to learn if it's really unitary or not non-unitary. But I guess you throw a quantum state and then recovering it is one very concrete way of checking this unitarity question. Any other question? Okay, if not, let's just... Yeah.